All right, so we're going to do two things today. First, last time we met, we were working on some examples of trig integrals. I'd like to do a few more of those, and then we're going to start the next section of chapter 3, which is 3C, and this is where we introduce something called partial fractions. Okay, so it's a very interesting idea, but first let's get back to our trig functions and see a few more examples. So this next one involves tangents and secants. Okay, so let's see. We have the tangent, the integral of the tangent of x over 2 times the secant squared of x over 2 dx, of course. All right, what do we do with this? Well, it appears that we'll be able to use u substitution. The question is how. So the way to think about it is that, first of all, we've got the tangent and the secant squared. So if you recall, the derivative of the tangent of x is the secant of x squared. So that's kind of a hint as to where we should probably take this. So why don't we try u equals tangent x over 2. And then if that's the case, then du would be, okay, so here's where we have to watch it. We have to use, because this is not x, okay, let me just get this out of here. I just want to quickly take a little bit of a detour here. If our function is the tangent, not of x, but of g of x, then what we have instead is the secant squared of g of x times g prime of x. Okay, so there's this rule that we have up here only applies to x. For anything else, for any other function of x, we're going to have tangent at g of x. The derivative is secant squared g of x times g prime of x. So here, what we're going to have is secant squared of x over 2 times 1/2, because of course, if you had something like this, the derivative of 1/2 of x is just x, 1/2 rather. So that is what we end up with here. Now, do we actually have that in our integral? Not exactly. We're close. We can provide the missing constant. It is not difficult. We've done it many times before. So here's what we'll do. We'll multiply the outside of this integral by 2, and the interior times 1/2. So now we do have u and du. Okay, so we got 2 integral u du. Okay, and so what does that leave us with? Well, based on the power rule, we'll have 2u squared over 2 plus c, or simply u squared plus c, plus c. And of course, since u was originally defined as tangent x over 2, that's our final result. So there's a couple of tricky parts to this. First of all, even if we're using u substitution, if we'd inadvertently chosen the wrong ones, u equals secant squared of x over 2, we would have realized pretty quickly that we do not have the du that we need. But the other tricky part was recognizing that the derivative of tangent x over 2 is not just simply secant squared x over 2. We do need to take into account the derivative of x over 2 through the chain rule. Okay, but now we're done with it. Excellent. All right, what's next? Ooh, this one looks like fun. Sine x cosine x dx. So again, we'll probably be able to use u substitution, but just a quick reminder, the derivative, the sine of x, is the cosine of x plus, well, in this case, it's just cosine of x. And the derivative of cosine x is negative the sine of x. So let's try this. U is sine of x. And if that's the case, then du would be cosine x dx. Well, it looks like we got it made. All we have is the integral of u du. Which of course by the power rule is u squared plus 2 over 2 plus c, which is now simply sine squared x over 2 plus c. All right. Now this next one, well, this one's going to be a bit trickier. So before we do it, let me just quickly remind you about our Pythagorean identities. So remember, there was 3 of them. We had originally but the one that we really need is well, actually, this should be enough for this one. All right, I was going to say the other 2 involve cotangents and tangents, but I think for this one we only need this Pythagorean identity. You'll see why in a second, because the problem is the integral of sine to the 5th of x cosine squared of x dx. All right, now whenever we have an odd power like this, the identities, if you notice, are only in terms of squares. So the odd powers are not going to help us. So why don't we try this? Let's try something like this. Okay, so remember that by the Pythagorean identity, sine squared x equals 1 minus cosine squared x. So here's something we should consider. What if we could do this? Oh, and by the way, this implies that sine x squared squared, which we can now write as one minus cosine squared x squared. Now we can solve this with FOIL. All right, let's try that. F is 1 times 1. O is 1 times negative cosine squared x. I is these 2, which is negative cosine squared x again. And then these 2 are last. So I'll have positive cosine to the 4th of 2x. Oh, sorry, not 2x, just plain x. All right, so what does that give us? Okay. Now, that would become this term. All right, so this is sine to the 4th of x, which is sine squared of x squared. And using the Pythagorean identity, we replace the sine squared of x with 1 minus cosine squared of x. When we square that, figure out with FOIL that this equals 1 minus 2 cosine squared x plus cosine to the fourth of x. So how is this going to speed things up? Well, let's find out. All right, well, there's no way I have enough room there. Let me just move this down. All right. So what does that get us? Well, why don't we try this? U could be, how about sine x? Or actually, no, let's try cosine x since we have so many of them. And du dx, or just du, could be written as minus sine x dx. Now, we have something like that here. We do not have the negative that we need here, though. So let's do this. And while we're at it, why don't we rearrange this a little? Okay, you can see where this is going. So in other words, I just provided the negative that I needed here, but in order to do that, I need to multiply by -1 out here. And now I've consolidated these two, and this came over here. So what I ended up with now is 1 minus 2u squared plus u to the fourth times u squared times du. All of this is du. Now I multiply these out. And then I can write each one of these individually. Actually, I'll leave this negative on the outside. Integral of u squared du minus 2 integral u to the fourth du plus the integral of u to the sixth du. And so let's see what we have. Okay, now we'll apply the negative sign across all these terms. Remember, we decided to call u cosine x. So there it is, after all that. So basically, we did two things. Well, first of all, whenever you have an odd exponent like this, because all the Pythagorean identities are in terms of squares, one thing you might want to think about doing is taking any term that has an odd power and rewriting it so that there's at least one term with an even power. And then see what you can do with the Pythagorean identities. The idea here is to try to reduce this all to either all cosines or sines, except for the sign that you need for the du. Okay, so in other words, the sine to the fourth was replaced with a squared Pythagorean identity. And then once that was done, by choosing u to be the cosine, we have everything we need. Du is this sine x with the negative. And so by doing some algebra and applying the power rule, we end up with our answer. So the strategy, like I said, usually the trig integrals can be done with u substitution as long as we are willing to do some algebra and make some substitutions to turn it into something more convenient. So it's finding something more convenient that's really the big challenge. And usually it involves the Pythagorean identities. And also it helps to know the derivatives of sine and cosine. All right, so this looked like it was going to be a catastrophe, and it wasn't that simple, but it is relatively straightforward. All right, now how about number 6? Now we're back to, no, this is still sines and cosines. What do we do now? All right, now remember, so let's try this. Oops. If we let u be the sine of x, then du is cosine x dx. That could be our du. So then what we have here is just simply u to the 1/2 power. By the power rule, we have u to the 3/2 power over 3/2, or 2/3 u to the 3/2 power. And then, of course, we replace the u with the sine x. And that's it. All right. Now, here's an interesting one. This one does involve secants and tangents. So let's just quickly remind ourselves, what is the relationship between them? All right, so if you took the derivative of the secant of x, you'll have secant x tangent x. If you take the derivative of the tangent of x, as we saw before, you'll get the secant squared of x. So if you look at this, you'll see that we don't have, well, what do we have? Well, let's see. Why don't we try this? If we let u be the secant, sorry, I missed one. Now this one's a little strange because you see what's going to happen. There is no u in there. All we have is du. Now, it kind of makes sense because when you think about it, if the integral of secant x tangent x is secant, that's the same thing as saying that the derivative of the secant is secant tangent x. So the two are just simply revert or inverses of each other. Okay, so in other words, if I differentiate this function with respect to x, it'll bring me right back to secant x tangent x. Okay, so Anyway, what else do we have here? Ooh, now this one looks scary. All right, now once again, we're going to need to lean on one of these Pythagorean identities. So what we could do is rewrite this as and when you apply FOIL, actually, we may not need FOIL for this one because, all right, let's hang on to that one. I'll just leave it like this. I think a better strategy, because when we're done with that, we're going to have a bunch of tangents and we won't have the correct du. So instead, let's try this. So given the derivative of the tangent is the secant squared. Why don't we try this? How about if we let u be the tangent? If that's the case, then what we are left with is 1 plus u squared du. And then we'll just have u plus u cubed over 3 plus c. And then we'll have tangent x plus tangent cubed of x over 3 plus c. Ooh, okay. So we can do a bunch more of these, but I think at least we've attempted to do several fairly messy cases so we can see some of the different techniques that can be used to solve these trig integrals. So, you know, like anything else, practice makes perfect, but after a while you start to recognize certain patterns. And of course, anytime you choose the wrong u, you'll notice it right away because the resulting expression will be much messier. Either that or it cannot be used to find du. So anyway, I'll be posting these, of course, as usual. In the meantime, it's time to get back to the new material. Now, this is something completely different. There's no, there could be trig functions involved here, but not necessarily. This is, what we're trying to do is take ratios, basically, of functions and find techniques for solving for their integrals. So we're using a technique called partial fractions. And that's because it's based on this notion of partial fraction decomposition. It's an algebraic trick for taking an expression and breaking it up into simpler components. All right, it's a little messy, but it's not that difficult. So first of all, let's see what this is all about. So imagine you had something like this, 3x over x squared minus x minus 2. Now, normally you would just leave it like that. But when you're integrating, this is very awkward to deal with. So it makes sense that we might want to break it up into smaller pieces. So how could we do that? Well, first of all, this expression is equal to x plus 1 times x minus 2. And you can double check that with FOIL. Just quickly do that. There's f, Here's O. Here's I. And here's the last. Okay, so in other words, this is correct. And how does this help us? Well, here's how it helps us. What we'll be able to do is the following. We're going to write it in a very strange way. We're going to break it up into two fractions, one of whose denominator is this expression, and the other whose denominator is this expression. Now, A and B are two constants that we're going to solve for. So yes, it may not seem like it, but we do have enough information to solve for both of them. So the first step is to give them a common denominator. All right, so how would that work here? Yeah, so originally it was this. So our common denominator is actually this, okay? So the way we can obtain that for x and a and b rather is to multiply this term by x minus 2 over x minus 2, and this one by x plus 1 over x plus 1. Now we're certainly allowed to do that because all we've done is multiply by 1. But now we have a common denominator, x plus 1, x minus 2, and now I can consolidate these two numerators as a times x minus 2 plus b times x plus 1. And since they have the same denominators, all I can do now is say, listen, this is equivalent to 3x equals a times x minus 2 plus b times x plus 1. That's interesting. Now, still, we have one single equation with two unknowns. And that's not enough, obviously. So what do? Well, first of all, we'll expand the right-hand side algebraically. So you can see I've applied the distributive property here. And I come up with ax minus 2a plus bx plus b. Now what I'm going to do is rearrange them. I could do this in a couple of different ways, but what I want is all the x terms here and the constants over here. Okay, so now what do I do? Well, the way this thing is written, let me just copy this to the next slide. There we go. Okay, so if that's the case, that tells me that 3 equals a plus b. And if you notice, there's no constant on the left-hand side. So that implies that this expression is equal to 0. So in other words, 3 equals a plus b, and 0 equals negative a plus 2a plus b. Well, now, all of a sudden, we have two equations and two unknowns, and we're all set. So we could do it in a couple of ways. Let's try this. Take that second equation and rearrange it algebraically, and now you have b equals 2a. And now you can go back to the first equation, which was 3 equals a plus b. You substitute b equals 2a. So you have 3 equals a plus 2a, 3 equals 3a, a equals 1. And now for the b, we can go back to the second equation, b equals 2a, and replace that a with a 1, and now you have your b as well. So going back to our original decomposition, we can just substitute a for 1 and b for 2. So all that work was just to take this expression and turn it into this. So why did we bother to do that? Well, because it'll be easier to find the integral of this piece than this piece. That's the only reason for doing this. In fact, this second term here can be found very quickly and easily with U substitution. So going back to the original equation, these two are now equal to each other. So we're going to integrate this term. Okay. So how would we do that? Let's look at the first term. 1 over x plus 1 dx. Let's try u equals x plus 1. Du would simply be dx. So that leaves me down here with 1 over u du. And by definition, this equals the log of absolute u, or log of x plus 1. Okay. How about the second term? 2 over x minus 2. Same idea. U is x minus 2. Du is dx. And so, by the way, I've also moved this 2 outside here. So you can see I also have 1 over u du, which is the log of u, absolute u, that is. And so I end up with 2 log x minus 2. And finally, after all that, I combine them, and this is my final answer. So the original expression was this. Now, that doesn't mean that this is the only technique that could have been used here. It's possible that we could have done some type of U substitution here too, but we need to understand this technique because there'll be many cases where this is not true, where this is really the only way to go. Now, here's a little hint, though. Just a quick review. The degree of an equation refers to the highest power of x. So just as an example, a cubic equation has degree 3. A quadratic equation has degree 2. So why does that matter? Because the partial fractions technique is really intended for cases where there is a ratio of functions such that the degree of the numerator is strictly less than the degree of the denominator. That's what it's meant for. Okay, so it needs to be a ratio. If there's no ratio, then there's no sense in doing any of this. There has to be a ratio of 2 functions to start with. And then it must be the case that the denominator's degree is higher than the numerator. Now, if that's not true, it doesn't mean we can't use this method, but we have to do something else. Otherwise, the only way that partial fractions can be used is to divide the denominator into the numerator and reduce the problem to 2 or more terms, all of which have, let's just put it this way, none of which have a higher degree Actually, this is very awkward to word it in English. Two or more terms which both satisfy, let's put it this way, which satisfy the requirements of the partial fraction technique. Okay. In other words, you can't just leave it like that. If you've got something like this, in a case like this, for example, here the numerator is divided by the denominator. And that's because the numerator's degree is higher. So now, by the way, I just want to remind you how this is done. What you can actually do is use a process which is similar to long division, x squared minus 4, 3x cubed minus 2x plus 7. So what you're going to do is find some term. We need to get rid of this 3x cubed. So something that would, which I multiplied by x squared minus 4. So I'm going to try 3x because 3x times x squared minus 4 equals 3x cubed minus 12x. 12x. So, oh, you know what, I just realized I put the wrong thing here. The 3x goes up here to indicate that this 3x, which when multiplied by x squared minus 4, gives me 3x cubed minus 12x. Now I'm going to subtract this entire expression. And now this is a negative number, so these drop out. This is now positive, so I'm left with 10x plus 7. Now, I can't go any further because 10x plus 7 has a lower degree than x squared minus 4. So what I've just demonstrated is that 3x cubed minus 2x plus 7 is the same thing as 3x plus 10x plus 7 over x squared minus 4. Now, all the terms have the requirement that the degree in the numerator, well, this first one isn't even a ratio, so we don't have to worry about it. But this one, the numerator is degree 1, and the denominator is degree 2. So now we can apply the partial fractions technique to what we have here. And so what we're essentially doing is breaking it up into two different integrals, and we'll treat each one separately. We couldn't do it directly the way it was in the first place. In other words, this will not lead us to the correct result. We have to go through the formality of splitting it up like this by using division. All right. So if that case comes up, then you'll know exactly what to do. All right. So formally, this is how we write it more formally. If we have a fraction, a function which is a ratio, in other words, a rational function, it's important that the degree of the numerator, p of x, is strictly greater than the degree of q, the denominator. Otherwise, we have to do something like division. Now here, there's no problem. Okay, we did the technique. And that was just fine. Now, now here's one. We're going to work through all the way. Starts out not promising. You can see the degree in the numerator is 2. Down here, it's 1. Oh no. So what we're going to do is use division to break this up into 2 pieces, both of which satisfy our requirements. So again, this is what we did. We have x plus 1 being divided into x squared plus 3x plus 5. So I start by multiplying by x because x times x plus 1 is x squared plus x. That gets subtracted, as you can see here, leaving just 2x. I bring down the 5, and now I'm going to try 2, because 2 times x plus 1 is 2x plus 2. That gets subtracted, and we're left just with the 3. So that means I end up with and now we're all set. Now we can apply the technique. All right, now this one, so we got 3 terms now. Actually, x plus 2 plus 3 over x plus 1, we'll split it up into 3 integrals, as we so often do. I moved the constants to the outside, and these first 2 can be solved with the power rule. This one, I need u substitution. So let's do that first. So let's let u be x plus 1, du is dx. So remember, the integral of 1 over u du is natural log absolute u plus c. And that's exactly what we have here. We get the 3 on the outside. U is our x plus 1, and du is just dx. So we got 3 times 1 over u du, 3 times log c. Oh, that's a typo. This should have been u. Okay, and then it's equal to 3 log x plus 1. Now, we're combining this with the other terms, so we don't need to worry about the constant just yet. All right. So, and just make a little note to myself to fix that typo. Okay. Very good. All right. Now, what about the rest of it? Okay. Well, the first 2 are easy. They're being solved with the power rule. So we have x squared plus over 2 plus 2 times x plus, and then this we just found with substitution, and we're all set. And of course, don't forget the c. The c you can save to the end. We've seen this before. When you're dealing with a very complicated indefinite integral, you can treat each one separately, but you really only need to apply the c when you're done, because no matter what those c's are, they're all going to be consolidated into a single constant anyway. And since we don't know what it is, all we're doing is acknowledging that there's a constant there. All right. Now, this next one is a lot messier. A lot messier, because it's going to have 3 components to it. How can you tell, by the way? Because the denominator is a cubic function. So we're going to end up with a over something plus b over something plus c over something. And that means it's going to be a lot messier to solve for it. Not impossible, but we have to be careful, because we're going to wind up with 3 equations and 3 unknowns. And unless we resort to matrix algebra, it means we basically have to rearrange, solve for one of the constants, and then substitute that into the other 2 expressions So this one is going to be definitely the most challenging. But the technique isn't any different. And also, if you notice, we're all set in the sense that the degree here is 1, and here the degree is 3. So we don't have to worry about that. The one thing we might want to worry about is how do we rewrite this? Remember, we have to rewrite it as a product of 3 functions of x. Well, let's note here that all 3 of those terms contain an x. So let's work with that. And if you notice, you recognize this is actually one we had earlier. So there are 3 components here. We can break this up, or factors. We can break this up into 3 factors. And so this integral can be rewritten. Actually, you wouldn't even need the integral. This expression, this partial, by the way, this partial fractions method can be used not just for integration. Anytime we have a fraction like this, if there's some reason for it, we can break it up using the partial fractions approach. So basically, what we're going to have is this. Okay, so this is where we're going. So we're going to have 3 constants to solve for. And of course, before we do anything else, we need to find a common denominator. That means each of these terms will have to be multiplied by 2 of these 3 factors. In other words, A will be multiplied by the ratio of this over itself, et cetera, et cetera. So it's going to be a bit more complicated. So I'll tell you what, why don't we save this for next time, because there's more that we need to do here with partial fractions. There's several more examples we need to go through. And I'd also like to then do some more practice problems and get some more practice, because this one isn't conceptually that difficult, but it can get very messy. Let's just put it that way. So here's what we'll do next time. We'll wrap this example up and we'll look at what follows, because what's coming up after this is basically more complicated versions of this. They're trying to give you helpful hints as to how to approach this when there's certain properties of the integral. And so we'll see. We'll check out each case as we go along. But we now know the basic concept of solving integrals with partial fractions. Okay, the basic logic won't change for the other cases. It's just that the results will get a little messier. So we'll knock it off here, and we'll pick it up again tomorrow with some more of these. Okay. All right. So I'll see you then.